Hello and welcome back to another episode of Disc Golf Physics. I want to talk about today why a disc skips when it hits the ground. And we're going to build up to next time talking about gyroscopic precession. We've been kind of building up to that over the last couple episodes. There is some math that's a little bit more difficult that's involved in some of these concepts, but today I just want to do sort of a conceptual understanding. And then next time I'm going to bring in a friend of mine in the physics department here to talk about gyroscopic precession and maybe a little bit more about why the pattern of the disc is the way it is, and get into a little bit more of that more difficult math. So in the last video we talked about moment of inertia and how because the disc's mass is concentrated mostly along the rim, it's going to have a higher moment of inertia than if it was evenly distributed throughout the body of the disc. And like linear inertia, which is just how much mass something has, the moment of inertia has to do with an object's resistance to change of its state of moving. So in linear inertia, just the amount of inertia something has, if I have a big heavy book like this and it's just sitting there, it's going to keep sitting there, and it takes a lot of effort for me to change it, and it won't do it by itself. It won't. If it's moving, it's going to keep moving. If it's not moving, it's going to stay sitting still, unless some outside force causes it to change. For rotation and moment of inertia, that's a resistance to the state of change of its state of rotation. So if it's spinning, it wants to keep spinning. If it's not spinning, it's going to continue to not spin unless something makes it change. In other words, the angular momentum, that's the moment of inertia times its rotational velocity, is going to stay unchanged. It'll be conserved. Remember, I think we've talked about conservation of momentum before, but the angular momentum is also conserved, and it will remain unchanged unless some outside torque causes it to change. So if it's spinning, it wants to keep spinning, and it wants to keep spinning the same way it was before. Now, when an outside torque acts on a spinning object, strange things can happen. Now, for a disc, I apply a force on it and cause it to rotate. If I'm on the plane of the rotation and I'm applying that force on that plane, it's going to cause a change in its angular acceleration. So torque causes angular acceleration just like a force causes a linear acceleration. So if I've got say my bicycle wheel here, I apply a force at some distance, some lever, it starts to accelerate angularly, it starts to spin. Or if I apply a braking force, I can stop it from spinning. But weird stuff happens when we try to change the angular momentum perpendicular to the plane of rotation. So if the bike tire is rotating like this, and if I try to reorient it like this and like that, some interesting stuff happens. Now, what does this have to do with disc golf? This is what happens every time my disc hits the ground. When it's spinning, the ground is going to apply a force like this. The plane of rotation is along the plane of the disc. The force is perpendicular to that plane. So an interesting thing happens, and I want to demonstrate it using this bicycle wheel. So I've got my bike wheel. I'm going to spin it, and if I let go, gravity applies a force. That force causes a torque that makes the bike wheel want to rotate around the pivot point of my hand. It's actually very similar to when a disc hits the ground. We'll get to that in a minute. So if it's not spinning, it causes rotation. If it is spinning, it causes rotation, but not the way we might expect. Now it's rotating perpendicular to the direction of the force. The force is trying to make it rotate like this. The torque that ends up happening causes the change in angular momentum to go like this. So how does that translate to a disc? Well, this was spinning kind of towards you like that. If I'm looking at it, it's counterclockwise. If I'm looking at it from above, it's going to be clockwise. A disc thrown right hand, backhand is going to be spinning if I'm looking at it from above, clockwise, just like my wheel. The gravitational force is making it rotate like this, very similar to a disc hitting the ground and having the ground push on it in that direction. So the wheel was spinning like this. The disc is spinning like this. I'm just rotating the whole plane 90 degrees. The ground is pushing up with a force that's going to be acting the same way as the gravitational force was on the wheel. So the disc hits the ground. I throw it, it hyzers in, hits the ground. The force is pushing up like this, but the change in angular momentum, the effective change in the rotation of the disc, is going to be like this. It's going to pop the front edge, the nose edge of the disc up, which is going to cause a flare skip. So if it's got a sufficient amount of spin and a good angle coming in so that the force is perpendicular to the plane of the disc, it's going to cause the front nose of the disc to pop up and give you a flare skip. Similarly, if the disc hasn't started hyzering yet and it's going forward and spinning, and the front edge is what hits. Now, remember before, if this edge hits, the nose flares up. If the front edge hits, then the right side is going to flare up and give us a skip that's going to kind of go off like this. So depending on where the point of contact is with the ground, we're going to get a different shape of the flare, the skip. Understanding how this change works can help us understand better how the disc is going to react when it hits the ground. Next time, we're going to talk about gyroscopic precession. So I hope you enjoyed it. I hope you learned something. Thanks for watching.